Okay, so carrying on from yesterday, the arrangement of electrons in atoms. And so that's what we're going to do today. We'll touch a little bit of what you did in some younger grades, but it's really just a lot more detailed. And so you have three rules that you need to know. And so write these three rules down. The first one is the Aufbau principle, AUFBAU principle. And in my writing, it's not the neatest writing. This principle says electrons enter orbitals of lowest energy first. And you already know this whether you realize it or not because you did this already. But electrons enter orbitals of lowest energy first. That's the Aufbau principle. The second rule is Hund's rule, which this is going to be new to you. It says that when electrons enter orbitals of equal energy, and the scientific word for that is degenerate, so when electrons enter degenerate orbitals, they do so one electron per orbital until all orbitals are 1/2 filled before placing the second electron. That seems complicated. It's really, really not, and I'll explain that out here in a second. And then the third rule is the Pauli exclusion principle, which says an atomic orbital can hold at most 2 electrons, which you already know from yesterday. But added to that, they must have opposite spins. Clockwise, we denote with an up-pointed arrow. Counterclockwise, we denote with a down-pointed arrow. And so those are the three rules that you need to know in order to write orbital diagrams and electron configurations, which is what we're doing today. And so, for example, let's go back here. When you were in 8th grade, you did something like this. Teacher said, hey, take sodium and put the electrons in sodium. And so what you would have done is you said, okay, sodium, you would have gone to the periodic table, you looked at sodium, you would have figured out that sodium has 11 electrons, and you said, okay, the first two go here in the first level. Well, you're following the Aufbau principle, which says electrons enter the energy levels of lowest energy first. Well, the first level is the lowest energy. So you kind of already knew that one. And then you would go up to the next one and you do 8 electrons in the next level. And then that would have been 10. So 2 in the first, 8 in the next would be 10. You got one more, you go up to the third level. And so you kind of have done this a little bit at a much more simplified form, if you will. Here's an energy diagram. I do not want you to write this, just want you to look at it as I talk about it for a second. And so energy levels are the energy levels themselves. As you go up, you go from energy level 1 to 2 to 3 to 4 to 5 and so forth and so on. Just like the rings in that previous slide. Energy level 1 is the lowest energy, energy level 2 is higher, energy level 3 is higher. Sublevels do the same thing. S is the lowest, and then P, and then D, and then F. And so what happens is, if you look at an energy diagram of the atomic orbitals and sublevels, you end up getting some overlaps. And so, for example, in the first energy level, we just have S sublevels, so there's one S. In the second energy level, we have 2 sublevels, S sublevels and P sublevels. And S sublevels are lower energy than P sublevels. S is lower than P. And so there's a slight difference here. And in the third energy level, we have the same thing. We need 3S, 3P, and 3D. What happens is the fourth S comes all the way down in between the 3P and the 3D. And so if you're putting electrons in atoms, you would not go 3S and then 3P and then 3D. You would go 3S, 3P, 4S, and then 3D. And there's more overlaps too. This is just the first time this overlaps. But there are other overlaps as well. The 5S comes way down in between the 4P and the 4S as far as its energy content. The 5P comes between 4D and 4F as far as its energy content. And so we see these overlaps and changes. And so I just wanted to show you this because the next slide is all of this summarized. And so let's look at that. This is a summary of the order in which electrons fill atoms in the energy order. And so we would start down here and you would go to 1S first. When you get to the end of the line, go to the next line. So you go 1S and then you go 2S and you go 2P and then 3S and you go 3P and 4S. And so you see, here's the overlap, 3P to 4S and then 3D. 3P to 4S and then 3D. So that's that first overlap, 3P to 4S and then 3D. And then 4P, and here's another overlap, 5S. And so this is just, it's called an orbital fill-in diagram. You ought to be able to replicate this, which you can because all levels have S's, all levels have 2 through 7 have P's, 3 through 7 have D's, 4 through 7 have F's. And you're just really going to do your diagonal lines, like for example, if we start here to 3D, you're going up 1 over 1. So 3D to 4s. Then you go up 1 over 1, 4p to 5s. So you make they're basically like these 45-degree angled lines that are parallel to each other. So write this down. You can pause and write this down, but I'm just going to go ahead and continue. And so we use this diagram to do orbital diagrams and electron configurations, which are just representations of where electrons are in atoms. And so an orbital diagram represents the orbitals. Remember, an orbital is what holds the electrons, and 2 electrons per orbital. An orbital as a labeled box, and the electrons as arrows. Up arrows for clockwise, down arrows for counterclockwise. So let's do an orbital diagram for, let's say, sodium, because we just looked at sodium a second ago. So sodium has 11 electrons that we're going to look at. Instead of placing them in the rings, we're going to place them in boxes. Now, where do they go first? According to our diagonal, they go to 1s first. And so we go to 1s. Now, we're going to label a box 1s. Now, it's s, which has 1 orbital, so we have 1 box. And we're going to put into that orbital 2 electrons, 1 up and 1 down, according to the Pauli exclusion principle. They must have opposite spins. And then after 1s is full, we'll move on to the next energy level or sublevel available, which would be 2s. And so 2s, it's an s, so s's have 1 orbital, and we'll put electrons in it, 1 up and 1 down. That's 4 over 11, so we're down to 7 electrons left. And then after 2s, we would go to 2p. Now p sublevels, you should know and remember that p sublevels have 3 orbitals. And so there will be 3 boxes. And these 3 boxes are collectively the 3p sublevel. Sorry, not 3p, 2p. Now, Hund's rule, this is where Hund's rule comes into play, which says, let's go back to it. Hund's rule says, when electrons enter orbitals of equal energy, they do so 1 electron per orbital until all orbitals are half filled before placing the second electron in. Now, these p orbitals, the 3 p orbitals, are of equal energy because they're at the same energy level, if you will, in the energy diagram. So Hund's rule applies here. Now, here's what Hund's rule, in simple terms, here's what Hund's rule is. Say you're going to get on a bus, a school bus, and there are people in some seats. You know, a school bus seats 2 people in each seat. Some seats have someone sitting in them, and some seats are empty. Where are you going to sit? Odds are you're not going to sit with someone in a seat if there's empty seats, so you're going to spread out. If you go to a movie theater and some people are already in the theater, you don't go and sit right next to someone if there's empty seats. You spread out. That's what Hund's rule says. Hund's rule says that when the electrons enter into these orbitals that all have the same energy, they're going to spread out. So we're going to go 1 up, 1 up, and 1 up. And now all of the seats have someone. We're going to start now sitting next to people. And so we'll come back and go 1 down, 1 down, and 1 down. Now that's 6 more electrons in this p, so we're down to 1 electron left. And where's it going to go? Well, according to the diagram, we're going to go from 2p into 3s. And so 3s is next. It's an s orbital. S's have 1 orbital, so 1 box, and we have 1 electron left, and we'll place it up. So this is an orbital diagram for sodium. We're going to do one more example of orbital diagrams before we do electron configurations. So let's do that. Orbital diagram. We'll do one for vanadium V, which has 23 electrons. Now, where are they going to go first? Well, they will first go into the 1s orbital, and we'll put 2 electrons in there. That brings them to 21 electrons. After 1s, they'll go into 2s, and we'll put 2 electrons in there. We're down to 19. After 2s, we'll go into 2p. P's have 3 orbitals, so 3 boxes. We'll put our 6 electrons in there. Shortcut, if you know it's going to be full, which we know these are all going to have 6. We have 19 electrons. We're going to put 6 here. We can put X's. They're going to be full. We can put X's in here instead of arrows. That's our 6 electrons. So 19 minus 6 leaves us 13 left. After 2p, we're going to go into 3s. That's going to be full, so we exit out. That's 11 electrons left after 3s. According to our diagram if you have that handy. We'll go into 3p. So p orbitals have 3 orbitals, or p sublevels have 3 orbitals, so 3 boxes. We have 6 electrons here. We have enough. That'll leave us down to 5 electrons left after 3p. According to your diagram, after 3p is 4s, and then after 4s will be 3d. So 4s, we'll put our 2 electrons in there. We're down to 3 left. After 4s is 3d. Now d sublevels have 5 orbitals. So we have 5 boxes. We only have 3 electrons. Hund's rule says, hey, let's spread out. We don't want to sit next to each other. So spread these electrons out. We'll have 3 electrons in the first 3 boxes, and the last 2 boxes will be empty. So that is a second example. That would be for vanadium. Now, electron configurations. It's very similar. It's a little, left off the end there, very little bit different. It shows the sublevel labels only. We don't show any boxes, just the labels. And we superscript the number of electrons is what we do. And so we can translate orbital diagrams into electron configurations. And so, for example, let's do a translation here. Here's our labels. So 1s, and how many electrons are in this 1s? Well, there are 2. So it's 1s superscript 2. 2s, and there are 2 electrons here. So 2s2. 2p, and there are 6 electrons in the 2p. So 2p, 6. And then 3s, and there are 2 electrons there. So 3s2. This is the electron configuration, or electron config. This is the orbital diagram. It shows you real similar information. Orbital diagram is a little more detailed than electron configuration, but very similar. So if we want to do the electron configuration for vanadium, well, we go 1s, and there's 2 electrons there, 2s, and there's 2 electrons there, this 2p, and there's 6 electrons here, so 2p6, 3s, 2 electrons, 3p, 6 electrons are in there, those are all full, so 6 electrons, 4s, there's 2 electrons there, and 3d, and in the 3d sublevel we just have 3 electrons, 1, 2, 3, so 3d, 3. That'd be electron configuration for vanadium. Now, if you don't already have an orbital diagram, you can still do it. You just follow the diagonal chart, and you know that, well, if it's an S, there can be 2 electrons in S's because there's 1 orbital. P sublevels, P's have 3 orbitals, so that's 2 electrons per orbital, or 6. D's have 5 orbitals. 2 times 5 gives you 10 possible electrons, and F's have 7 orbitals, or possibly 14 electrons. And so these are the maximum numbers that can be in S, P, D, or F. And so if we have a atom, let's say we wanted to do calcium, and we don't have the orbital diagram to do the translation, we can still do it. So where do they go first? Calcium has 20 electrons. Well, they first go to 1s, and how many can an S hold? Well, S can hold 2 electrons. So now we're down to 18. After 1s, they go to 2s, and that can hold 2 electrons. So now we're down to 16. After 2s, we can go to 2p. P can hold 6, so we're down to 10 electrons. After 2p is 3s. S can hold 2, so we're down to 8. After 3s is 3p, which p can hold 6, so we're down to 2. And after 3p would be 4s, which can hold 2, and we're done. There's our electron configuration for calcium. 1s2, and you just read it like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's how you would read that configuration. All right, so do a few practice ones. Do like carbon and magnesium, and how about titanium? Just do a few practice ones. Grab a few elements, practice them, compare them with the people who you're with, and see if you can get these right. All right. Hope to see you guys soon.